So in the last question, we had stopped just short of non-rigid transformations. We graphed the square root of x, and then we said, okay, let's look at what happens when I put a 2 in front of that. We were talking about changing the shape of the graph. In the previous ones, even with like horizontal shift, vertical shift, reflections, whatever we did, all we had done to the graph is literally just move it or flip it upside down. Or not necessarily upside down, but reverted or inverted. So it's like it looks like it's going, instead of left to right, it's going right to left, and vice versa. But what we had not done is change the shape of the graph. It's still the parent function. It's still a square root for the last example we did. However, when we put a number in front of it, we're now changing the shape. It's called a non-rigid transformation. It's going to distort the graph slightly, depending on how big the number is. Now, when it comes to the graph of g of x, this is going to stretch the graph vertically. If you put a number in front of the function, just like we did with the square root, it's going to be a vertical stretch. Literally, like you picked up the top of this thing and you said, I'm going to pull this straight up. It's going to stretch it if that number happens to be greater than 1. It's going to shrink the graph if that number is less than 1, but also has to be greater than 0. That number falls between 0 and 1. Why do I stop at 0 and not just say, okay, if it's less than 1? Meaning, what if it's like negative 5? Is that going to stretch or shrink my graph? You have to keep those two separate. For example, if the number was negative 5 f of x, this is, in fact, a number that is greater than 1. So the 5 is going to stretch. But we cannot take a look and say that's negative 5 though, because what does the negative do? It is going to reflect. You have to take those two as two separate transformations. We look at the number itself, so you almost want to look at the absolute value of the number to decide whether it's vertical stretch or shrink. If it's more than 1, it's going to stretch. If it's less than 1, or basically between 0 and 1, it's going to be a shrink. Keep that in mind. That's one of those things that sometimes will throw us off. A negative does not stretch or shrink. A negative reflects. The number is what's doing the stretch or shrink to the graph. Non-rigid transformations is by the number only, not by the sign of the number. That's a separate transformation. Then, when we look at a graph of h of x, and again, just another function, if that transformation, that non-rigid transformation, that c value, that number, is inside with the x, it is going to be a horizontal shrink when it's greater than 1. Greater than 1 is going to shrink. It's backwards. It's stretched vertically if it's more than 1. It's going to shrink if it's more than 1 now, but it's going to shrink horizontally. Again, it happens to the x. So just like we mentioned before, and it's just a good rule of thumb, if it happens to the x, it's happening inside, and inside it's going to be opposite. Opposite of what we think. Plus goes to the left, minus goes to the right. Well, then if I'm multiplying, I'm really shrinking this thing. Likewise, it's going to stretch it horizontally. Like literally, if you were to take the two ends or whatever the graph is and pulled it sideways, you're stretching it vertically. If that number happens to be between 0 and 1. For the same reason, if we put a negative inside, the negative is a reflection. You have to take that separately from the number that's multiplying that causes the stretch or shrink. Also, keep in mind, why is it opposite? For the same reason, if you're solving for x, you're doing the inverse operation. So a multiplication looks like it's being divided. It's getting smaller. So it's going to shrink if that number is large. But if you have a fraction in front of it, you multiply. And so it looks like it's bigger when you have a fraction. It's going to look smaller when you have a larger number. So yeah, just general rule of thumb, inside is the opposite. All right? Take a look at a couple of these here. What is happening to each parent function? Look at the first one, the absolute value of x, the parent function. We put a 3 on the outside. It looks like I took my numbers 0, 0, 1, 1, and then negative 1, 1. And I took each one of those and pulled it upwards. It's like I took the blue and said, I'm going to stretch this upwards. Same thing here. I'm going to stretch this upwards. It is a vertical stretch. For the next one, 1/3 is on the front of this thing. So here's our original points again, where we have 1, 1, 0, 0, and then negative 1, 1. But this time, I put a 1/3 in front. That means it's going to be 1/3 as tall. It's like you basically just took the graph and you sat on it. And now it's going to compress it. It's going to push it down. This graph is now smaller. It's going to shrink vertically. Now, you're probably thinking too, oh, maybe I just stretched this horizontally. And that's fine. You can call it that. When it comes to transformations, though, the easiest thing to do is to apply that as a vertical transformation. When it comes to stretching or shrinking a graph, it's best to talk about a vertical stretch, a vertical shrink or compression, and just try to avoid the horizontal because that's a little trickier. It can be done, but that same horizontal transformation, a non-rigid transformation, can be the result of a vertical transformation as well. So in this case, if I wanted to say, oh, I just know I squeezed it horizontally, that's fine. You can call it that. You can have said for this first one that, oh, no, I didn't stretch this vertically. Instead, I just took that point and moved it inside. That's fine. It's just it's trickier to represent that with an equation. So just keep that in mind as well. You can read a horizontal transformation, but if you're going to decide on what happened, it's better to talk about it in terms of vertical stretch or shrink. So that brings us to the end of this section. We are going to be doing an assignment on page 72. There are your problems. I gave you the even problems. This is one of the very few times I do that. And the reason for that is because I want you to try these by hand without like really just seeing what the graph looks like, because really the graph is the answer for most of these. So I needed you to show me a little bit of work and how you're creating these graphs. And I do want you to hesitate when it comes to graphing these with any graphing utility. I want you to practice graphing these by hand. This is something that can be done fairly easily if you apply transformations to the parent functions.